In this video, we are going to discuss the phase shift of trig functions. The phase shift of a wave is the horizontal distance from the origin at which the positive half cycle of the curve starts. Given the general sine function, y is equal to a times sine of bx plus c, we can consider the effect of coefficient c in this equation, and it will either move your function to the left or right depending on whether or not c is positive or negative. Recall in Module 1 we looked at transformations of functions. We had transformation where g of x was equal to f of x plus c. When we have x plus c within a function, we know that we have a shift to the left when c is greater than 0, and we have a shift to the right when c is less than 0. We can describe the magnitude of this shift by describing it as a phase shift. To determine the distance from the origin, given our general equation, we use the formula for phase shift that the phase shift is equal to minus c divided by b. Whenever b does not equal 1, it means our trig function is not only being shifted, but it's also being stretched or compressed. The phase shift accounts for the stretch and compression as well as the shift all in one calculation. When we calculate the phase shift, if you get a negative value for the phase shift, it means your graph is shifted to the left, whereas if you get a positive phase shift, it means your graph is shifted to the right. Now determine the phase shift for the following function. We have the function y is equal to sine of x plus pi over 2. Consider the coefficients in front of sine, which in this case would be 1, as well as x would also be 1, which give us our a value, our b value, and we can see our c value is positive pi over 2. Now to calculate the phase shift is equal to negative c divided by b, which is negative pi over 2, divided by 1, which is equal to negative pi over 2. The resulting graph of this function is given below. Right now this function just looks like the cosine function, but if we consider the original function sine of x before the shift occurred, you can see how we arrived at this graph. Sine x has zeros at 0, 2 pi, as well as pi. The maximum value occurs between 0 and pi, and the minimum occurs between pi and 2 pi at 3 pi over 2. And so we can connect this using a smooth line. And this is the graph of y is equal to sine of x. So we didn't need to account for any change in the magnitude or in the amplitude or the period, but this function is phase shifted. So our phase shift is negative, which means we're going to go left pi over 12 units. So each of these values in our sine x is going to move to the left pi over 2. And you can see here we arrive at our shifted function. Okay, so the blue line is y is equal to sine of x plus pi over 2. Which is in fact the same as our cosine function. So if you take the sine function and shift it to the left by pi over 2 units, you do get the cosine function. In this next example, we want to calculate the amplitude, period, and phase shift of the following function and then sketch it for one cycle. What we can do is make an initial sketch without the shift and then perform the shift after. The function we would be graphing without the shift is f of x is equal to 2 sine of 3x. Let's first consider the amplitude, period, and phase shift of the function given. Our amplitude is equal to 2. The period is equal to 2 pi divided by our b value, which is 3, and that can't be reduced any further. And the phase shift is equal to negative minus pi over 4 divided by our b value of 3. So those negatives cancel out. We end up getting pi over 4 divided by 3, which is pi over 12. So let's draw our axes. Let's consider our values along the x-axis. To show one full period before the phase shift, we need at least one full period, which is 2 pi over 3 values. We mark down a full period at 2 pi over 3. Halfway along the x-axis is pi over 3, and then we can subdivide further at pi over 6 and pi over 2. Now sketching 2 times sine of 3x, we know that sine at 0 is 0. Zeros will occur at 0, pi over 3, as well as 2 pi over 3, and then we have max and min values in between those. Now consider a nice smooth curve connecting these points, and we get the equation and graph of y is equal to 2 sine of 3x. When we calculated our phase shift, we found the phase shift was positive pi over 12, which means we have to move our function to the right pi over 12 units. Okay, so each of these points on our graph, we're going to move to the right pi over 12 units. We have pi over 12 showing here, 2 pi over 12, which is pi over 6, 3 pi over 12, pi over 4, 4 pi over 12, which is pi over 3, 5 pi over 12, 6 pi over 12, 7 pi over 12, 8 pi over 12, which is 2 pi over 3, and the last one is 9 pi over 12, which is 3 pi over 4. When we shift each of the critical points to the right pi over 12 units, we end up getting the following values, and we can sketch our smooth curve to show the shifted graph. And the way that I've graphed this, I mean, it's not perfect, but you can get a good idea of what's happening with our equation. It's always a good idea when you do work like this to compare it to Desmos or some other graphing tool in order to check your work. Now we have another equation, y is equal to 3 times cos of 2x plus 30 degrees. Note that our phase shift is provided, our c value is provided in degrees, and therefore we should describe our period as well as phase shift and all the values on our x-axis in degrees. One thing that we would need to remember to use our formulas is that 2 pi is equal to a full way around the circle, and that's 360 degrees. We can calculate the amplitude, which is 3, the period, which is 360 degrees, divided by our b value of 2, is equal to 180 degrees, as well as our phase shift, which is negative c divided by b, or negative 30 degrees, divided by 2, minus 15 degrees. Now we can sketch the curve, make sure that your y value accounts for your amplitude, your y-axis, and the x-axis should show at least one full cycle and account for the fact that we will be shifting the whole thing to the left 15 degrees. Our period is 180 degrees, but we're going to account for that using increments of 30, showing 180 degrees. We can divide that in half by showing 90. Don't forget we have 30, 60, and so on. So we have enough values on the x-axis now to show one full period. So don't forget, this is a cosine function, so before our function is shifted, it has a maximum value occurring at x equals 0, and at one period, so x equals 180, your max will also occur, and the minimum will occur at 90 degrees, so halfway between those maxes, and then we have zeros in between the max and mins at 45 and 135 degrees. So there's an approximate graph of y is equal to 3 cos of 2x. Now we want to show the same thing, same graph, but taking into account the phase shift. So the phase shift is negative, therefore we're going to go left by 15 degrees. So each of the points in this graph will shift to the left by 15 degrees, which happens to be half a square. And when we graph, we get the following curve, which represents y is equal to 3 cos of 2x plus 30 degrees. Next, we have a couple practice questions. So determine the phase shift of the curves below and note the phase shift on the graph. Okay, so we have a graph that is provided for 3 sine of 2x, and we want to calculate the phase shift. Okay, so we take a look at this, putting it into general form, we get 3 times sine of 2x. Our c value happens to be 0. Therefore, our graph isn't shifted at all, and its phase shift is equal to 0. So you can also get that by calculating it. So c is equal to 0, b is equal to 2, and a is equal to 3. So your phase shift is minus c over b, which is 0 divided by 2, which is 0. Okay, so we can't actually show the phase shift on this graph since it was not shifted at all. Whereas in question 2, it says, determine the phase shift of 3 times sine of 2x minus pi over 2. And we can calculate that. So identify ABC. So your phase shift is equal to minus c over b, which is minus negative pi over 2 divided by 2, which is pi over 4. We can write down what pi over 4 is. As a decimal, it's approximately 0.78540, and this is a sine curve, so normally you would have a point at 0, 0, and it's been shifted by pi over 4 units. So each and every single point that would normally be there, so the zeros have all been shifted to the right by pi over 4 units. We have another example here that says find the phase shift for y is equal to sine of x minus 3 pi over 2. From quickly examining this equation, we see that a is equal to 1, b is equal to 1, and c is equal to negative 3 pi over 2. Therefore, our phase shift is equal to negative 3 pi over 2 divided by 1, or just 3 pi over 2. We know from what we learned in Module 1, because we have a negative value here within the equation, that our phase shift will be to the right, and that's what we've also calculated, to the right. So this means that the positive half cycle of the curve starts at 3 pi over 2 radians to the right of the curve, y is equal to sine x. In the next video, we'll be looking at the midline shift, and then we'll be putting it all together, going back and forth between writing an equation based on a graph and graphing based on an equation.